Right, today we start looking at chapter 11, which takes those ideas of aqueous solutions that we looked at in chapter 8 and starts to rethink them and start to apply some of those concepts into some other kinds of physical properties that we call collectively the colligative properties. Now, before we get fully into colligative properties, there are some things that we need to go over and review. So, in the last chapter, we saw a number of different ways to express concentration. We could express concentration by molarity. Remember, molarity was the number of moles of solute divided by liters of solution. We also saw these ratio-based, mass ratio-based, where we had mass of solute divided by mass of solution, and then multiplied by some factor x that defined the concentration. So percent we multiplied by 100, parts per million we multiplied by a million, parts per billion we multiplied by a billion. But all of these concentrations here have limitations associated with them. Let's take molarity, for example. Molarity is a very common concentration unit. We see it used all the time in laboratory, especially. The problem is it is a volumetric-based unit, has a volume here in the denominator. And as you know, when things heat up or cool down, their volumes do change. Even if it's imperceptibly small, there is still a change in volume. And if we have significant enough changes in volume, that means that molarity can actually vary with temperature, which means a 2 molar solution at one temperature might actually only be 1.9 molar at a different temperature. So we have to take molarity with a little bit of caution if we are dealing with solutions that have wide varieties of temperature conditions associated with them. And so to combat that, we actually will introduce another unit of concentration known as molality. Molality takes out that contribution of volume by changing the denominator from liters of solution to kilograms of solvent. And since moles and mass are both held under laws of conservation, molality is not going to change with temperature. It's not going to be temperature dependent in any kind of way. And we're going to use concentrations in molality when temperature changes are expected or are at least possible. Now, there is a common conversion here that we can use that will help us to go between molarity and molality. And that is, if we know the density of a solution, we can calculate molarity and molality from each other. We just have to follow kind of a simple protocol. And so you might recall from chapter 8, we saw this kind of protocol when we were looking at converting between molarity and mass percent. Now we see it here again with our conversion between molarity and molality. The only difference here is that there's going to be a little bit extra involvement, and we're not going to be able to fully use dimensional analysis to solve the problem. But we're going to be able to use dimensional analysis to solve a good chunk of it. But once again, knowing your definitions really makes a significant difference in terms of getting the right answer and the right interpretation, or the wrong answer and the wrong interpretation. Let's take a look at an example. First example here, determine the molality of a 0.194 molar nitric acid solution if the density of the solution is 1.1 grams per milliliter. Now, we've covered problems like this before. What we want to make sure that we do in these kinds of problems is ensure that we have our definitions correct. And so our molarity indicates that we have 0.194 moles of nitric acid for every 1.00 liters of solution. We also know that our density indicates that we have 1.10 grams of solution for every 1.00 milliliters of solution. Now, these are important factor labels here. I want you to pay special attention to them because this is probably where the majority of mistakes in these kinds of calculations are made, where we use density to do things for solvent, or we do density for things of solute instead of solution. Density is referring to solution and solution only. So let's take a look at how we would approach this problem. Now, again, knowing our units plays a significant role. I have moles of nitric acid per liter of solution right now. I want to convert this to moles of nitric acid per kilogram of water. That's my goal here. And so I can see that already I've got something in common. I've got my numerator already in common in both of these. The question is, how do I use the information that I have to turn the liters of solution into kilograms of water? Well, again, having our definitions in mind is going to play a significant role in solving this problem. If I start with my simple definition, 0.194 moles of nitric acid in 1 liter of solution, well, I can take this in a couple of ways. I can take that number of moles of nitric acid, turn it into grams of nitric acid, and I can take that liters of solution and turn it into grams or kilograms of solution. We'll just go with grams. And so if I know the grams of solution and the grams of nitric acid, grams of solution minus grams of nitric acid would give me grams of water, which I could then convert to kilograms of water for the denominator. And so that's exactly what I'm going to do. I just need to do a couple of conversions to help me get to this spot. So my 0.194 moles of nitric acid, well, dimensional analysis, I just need a molar mass. 1 mole of HNO3 is 1.01 for hydrogen, 14.01 for nitrogen, and 3 times 16 for oxygen. 63.02 grams is my number there. And so I put that in and I solve, equals 63.02 times 0.194 would give me 12.2 grams of nitric acid. The second conversion I need to worry about is the conversion of 1 liter of solution to grams. Now I can take advantage of this in a number of ways. Easiest way to do it would be to convert the liters, 1 liter, into milliliters, 1,000 milliliters, and then convert the milliliters, 1 milliliter, into grams, 1.10 grams of solution. And if I follow that all the way through, 1 times 1,000 times 1.10 would give me 1,100 grams of solution. Following the equation, I've got 1,100 grams of solution minus 12.2 grams of nitric acid. 1,100 minus 12.2 would give me 1087.8, rounding to sig figs here. I'm going to call that 1090. So I've got 1,090 grams of water, which I could convert, divide by 1,000. That's 1.09 kilograms of water. And so the molality would equal my moles, which is still 0.194 moles, because I've based all of my calculations on that number being present, divided by 1.09 kilograms, and 0.194 divided by 1.09, I get 0.178 molal, little m, HNO3. So that's how you do these kinds of calculations. Really kind of straightforward stuff once you kind of get into the groove of knowing what to do with it. But as you might expect, it's going to take some practice to get you to that spot, and get you comfortable with doing this and knowing what to do when. So we'll stop this here. I'm going to post a second video of another type of conversion between molarity and molality. And with that, we're going to call it a session right here. Have a good day.